For centuries, physics relied on the idea of a clockwork universe. In this model, time ticks at an identical rate for every observer, and space functions as an unbending stage where events play out. This world follows the rules of velocity addition. If you stand on a platform moving at 50 miles an hour and launch a ball forward at that same speed, someone standing still on the ground sees that ball traveling at 100 miles an hour. The speeds combine perfectly. This logic holds for every physical object we can touch, but it fails for light. In the late 1800s, experiments revealed a massive anomaly. The speed of light remains 186,000 miles per second, regardless of the motion of its source. Physicists tried to model this using familiar concepts. They tested if light behaved like a bullet fired from a boat, where the speeds are additive, or like a fish released into the sea, which swims at its own independent speed, ignoring the boat's motion entirely. Light defies both models. If you shine a light from a speeding train, you see it move away at the standard speed. But an observer on the tracks, even one chasing the train, measures that same beam of light moving at the exact same constant speed. It refuses to stack with any other velocity. This refusal to change speed creates a logical crisis. If the speed of light is an absolute constant that never wavers, then our definitions of space and time are the variables that must bend to keep the math consistent. In 1905, Albert Einstein abandoned the intuition of the past. He chose to trust the absolute speed of light and used it as a tool to interrogate the nature of time itself. He imagined a high-speed train rushing past a stationary platform. This became the setting for a thought experiment that would unify space and time. Suppose two lightning bolts strike the front and back of the train. For an observer standing on the platform exactly halfway between the strikes, the light waves travel equal distances and arrive at the same time. To this observer, the strikes are simultaneous. Now consider a passenger inside the train. Because they are rushing toward the front bolt and away from the rear one, the light from the front strike hits their eyes first. Since the speed of light is constant for everyone, the passenger correctly concludes that the front bolt struck before the back one. Both observers are right, yet they disagree on when the events happened. This proves that simultaneity is relative to your motion. Time does not pass at a universal rate. It is a personal measurement tied to your perspective. Einstein's math combined these shifting perspectives into a single four-dimensional fabric. He called this entity spacetime, a domain where distance and duration are inextricably linked. This special theory only explained objects moving in a straight line at a constant speed. Einstein spent the next decade trying to understand how this new spacetime reacted to acceleration and the mysterious pull of gravity. He began with a person inside a windowless elevator car, isolated from the outside world. If a rocket pulls the elevator upward through empty space, the floor pushes against the passenger's feet. If the elevator sits on the Earth's surface, the force of gravity produces the exact same sensation. Einstein realized that the physical effects of acceleration and gravity are indistinguishable. This equivalence principle meant that any odd behavior seen in an accelerating frame must also occur in a gravitational field. Imagine a beam of light crossing an accelerating elevator. Because the car is rushing upward, the light appears to follow a curved path toward the floor. If gravity is equivalent to acceleration, then gravity must also bend light. Since light always follows the shortest possible path through the universe, a curved beam of light reveals that the space-time through which it travels is itself physically curved. Gravity is the geometric shape of the universe. Massive objects warp the space-time grid, and that curvature dictates how light moves through the void. Einstein finalized these ideas in 1915, in a world being torn apart by the First World War. The mechanical optimism of the previous century had resulted in the chaos of trench warfare, leaving the public searching for new ways to understand a broken reality. When observations confirmed that gravity truly curved the light of distant stars, the news hit a traumatized society. The discovery that even time and space were relative felt like a scientific confirmation that absolute fixed truths were a thing of the past. This shift influenced the rise of anti-reason art movements like Dadaism. Artists began creating works that mirrored the disorientation of relativity, presenting multiple conflicting perspectives of a single object simultaneously. Relativity became a defining lens for the 20th century. It demonstrated that human intuition, the common sense shaped by our local environment, is a limited and often misleading guide to the actual behavior of the universe. Today, we view the universe as a dynamic, four-dimensional geometry. It is a structure shaped entirely by the matter and energy within it, expanding from a singular point billions of years ago. By following the logic of moving trains and falling elevators, Einstein provided the tools to understand the most extreme phenomena in the cosmos, from the birth of galaxies to the center of black holes. This transition from simple thought experiments to a comprehensive map of the cosmos represents a unique achievement of human reason. We translated our most basic observations into a description of the universe's physical shape.